Okay, guys, so today we're going to talk about 9.2 inverse functions. This might be a little bit longer section in terms of a lot of definitions and graphs and stuff because we kind of want to see the relationship between inverse functions. And then some of the stuff that we learned in 9.1 in terms of composition of functions is going to come back to help us a little bit, okay? So here's what we're going to try to talk about. Determine whether a function is a one-to-one function. Use the horizontal line test to decide whether a function is a one-to-one function. So we know that the vertical line test can test if something is a function or not. Now we're going to learn that the horizontal test can tell us if something is one-to-one. Find the inverse of a function, find an equation of the inverse of a function, graph a function and their inverses, and determine whether two functions are inverses. So we're going to use composition of functions, but there's a lot of ways you can actually determine if two functions are inverse, but we're going to try to use composition of functions to help us with part F. Okay. So it says one-to-one functions. So we have studied functions which are defined to require that each element of the domain or the input values produce a unique element range or the output values. For a one-to-one function, each x value input corresponds to only one y value output, and each y value output corresponds to only one x value input. So basically, a one-to-one function is a function, but it's even more particular. It wants to even be more. So if we were doing a mapping like this, and I had 1, 2, 3, and then here I had 4, 5, 6, and I did this mapping like this, this would be one-to-one because it says each x value corresponds to only one y value, okay? So, and it goes back the other way. So that's kind of how it is for functions, right? But then it says each y value corresponds to only one x value. So this would be one-to-one. And by the way, you can write one-to-one like this. This is a one-to-one relationship, okay? Now, if we had something like this where we said 1, 2, 3, and then, we went, 5, 7, 9, I don't know, just go with it. And then we did this mapping where we went from 1 to 5, from 2 to 7. You know what, let's do this. And then let's go from, you kind of can't see that too well, sorry about that. 2 to 7, and let's go from 3 to 7, okay? So is this still a function? Well, the answer is yes, because each x value corresponds to one y value, but not the other way. It doesn't go backwards. It doesn't say, well, each y value only corresponds to one x value. It actually corresponds to two different x values. So yes, this is still a function, okay? But it is not a one-to-one function, okay? So this is not what we're looking for in this section. So we want to learn about one-to-one because it'll help us talk about inverse functions, okay? So determine whether each function described is one-to-one, okay? So again, does each x go to one y and each y go to one individual x? So for this first one, we see 1 goes to 2, 3 goes to 4, 5 goes to 6, and 6 goes to 7. So yes, this is a one-to-one function since each y value corresponds to only one x value. Now we see here that the 3 goes to 7, right? And this 6 goes to 7, okay? So this is still a functional relationship, but it is not one-to-one because the 3, if we had this mapping, we would have 0, 3, 6, -2. And then here we would have 3, 7, -2. And so we would have -2 goes to -2. We have 6 goes to 7. We have 3 goes to 7. And then we have 0 goes to 3. So right here, this is what would break it, right? We see this relationship right here is what's causing the problem because we have one y value going to two x values. So even though it still is a function, it is not a one-to-one function, okay? And sometimes if you guys get confused, that's what I do is I draw these little bubbles and then draw it out, okay? And then you can see they have a little nice explanation right there of what I just did. So if we have a graph of something, of some function, we can very quickly determine if it's one-to-one by passing the vertical line test. I'm sorry, the vertical line test to determine if it's a function, and now also the horizontal line test to determine if it's one-to-one. So similarly, a one-to-one function must satisfy the horizontal line test. If every horizontal line intersects the graph of a function at most once, then the function is one-to-one. So basically, you can only touch it once with a horizontal line. So the moment you see right here, right there, there's a horizontal line that cuts right through this parabola, and it is not a one-to-one function. So it does pass the vertical line test, right? But it does not pass the horizontal line test. Anywhere I draw a horizontal line, or almost anywhere, it'll cross it more than one time. So this is not a one-to-one function. Now, if I draw a horizontal line here, yes, this is definitely a function. But now if I draw a horizontal line here, it's okay. What if I draw one here? What if I draw one here? Anywhere that I want to draw a horizontal line, it'll only touch the graph one time. So this is in fact a function, and it is also one-to-one. So we say this is a one-to-one function. Or you can do the book, I think, says like this. Ooh, that's really bad. Either way to say it is fine. Okay, so hopefully you guys are kind of getting the hang of that. Now, does this pass the horizontal line test? Yes, it does. However, this is not a function because it fails the vertical line test. As you can see, they have their vertical line right here. I just like to draw a bunch of them. But yes, this fails the vertical line test. So it's not a function, okay? And we're looking for one-to-one functions. That's what we want to deal with. So note that while we previously discovered that a horizontal line represents a function, it is not a one-to-one function. It will not pass the horizontal line test. So that's just for the basic horizontal line. Obviously, it doesn't pass the horizontal line test because you draw one line right on top of it and you touch it in infinite places. All right, so inverse functions. This is kind of why we're learning a little bit about one-to-one so we can deal with inverse functions. Okay, so for each one-to-one function, we can find an inverse function by switching the coordinates of the ordered pairs of the original function. So I'm going to read all this, and then it'll make more sense when we actually do one. So for a particular function f, the notation for f inverse for the inverse function is f inverse. So this is how we're going to write. It does not mean the reciprocal. It's not 1 over f. This is notation that we use to say this is the inverse function f inverse. The inverse of a one-to-one function f is the one-to-one function f inverse that consists of the set of all ordered pairs y comma x, where x comma y belongs to f. So basically, by switching the coordinates, it does something special to the relationship between the function and how it's built. The way an inverse function is built creates a special relationship between its original function and the function that it's an inverse of. Okay, so we'll see how that works. So here they're just showing you very quickly, just with coordinates. If this is some function g, then here would be g inverse. So notice they literally take 3 and put it in the y coordinate, and they take 4 and put it in the x coordinate. They take 6 and put it as a y coordinate, and they take 2 and put it as a x. So notice they're just interchanging the x's and the y's, or interchanging the x's and the y's, so you can very quickly see that that would also change perhaps the domain. So if the domain of this particular function g, the domain of this would be the set of what 2 comma, well, I'll write it out of order just so we can kind of line it up. 3 comma 6 comma 2 comma 4, and the range would be 4 comma 2 comma negative 3 comma negative 5, right? So this would be the domain and range of G. Okay, so if I wanted to do the domain and range of G inverse, here's the domain. The domain would now be 4, 2, negative 3, negative 5. And the range would now be 3, 6, 2, 5. Now, if you notice, if we look right here, the domain was 3624. I'm sorry, I messed that up. 36, I looked at the wrong one. 3624. Okay, so if you notice, the domain of G is 3624, and now it's the range of G inverse. If you notice that the range of G was 4, 2, negative 3, 5, it is now the domain of G inverse, which makes sense because how did we build the inverse? We interchange the X's and the Y's. So then, of course, that's going to interchange the domains and the ranges for each of these functions. Okay, so just to keep that in mind, that's one way you can kind of think of or a relationship that is built between a function and its inverse is the domains and range flip-flop. Okay, so finding an equation of the inverse of a one-to-one function. If a one-to-one function is defined as a set of ordered pairs, we can find f inverse by interchanging the x and y coordinates of the ordered pair. So here's what we're going to do. We're going to do these 4 steps. Step 1, we're going to replace f of x with y. So just as a notation, we're going to interchange x and y. So we're going to put all the y's where there were x's and put all the x's where there were y's. And then we're going to solve again for y. And then we're going to replace y with f inverse, okay? So this will make a little bit more sense here. So this is a relationship. So let's take a look at this problem. It says, find the equation of the inverse of f of x equals 6x minus 1. So we're going to take this and we're going to say, okay, replace f of x with y. So this is going to be step 1, y equals 6x minus 1. Now it says interchange x and y. So this will become x equals 6y minus 1. Notice I just flip-flopped where the x's and y's go. Now we have to solve for y. So I'm going to move the 1 over, and I have x plus 1 equals 6y. Then I'm going to divide by 6, divide by 6. So I now have y equals x over 6 plus 1 over 6. Right? So let me just double check, make sure I'm doing everything okay. No silly mistakes anywhere. Or you know what, we could just write it like this. So this would be x plus 1 over 6. I'll just leave it like that, which is equivalent if we went to graph it 1 over 6. Now it says replace y with f inverse. So this becomes f inverse of x equals x plus 1 over 6. And this would be the inverse of f. So now they say to graph it. So luckily, I left the graph here because anytime you're going to have to start graphing 1/6, that's going to be really tough to graph. So if we graph f of x, 6x minus 1, right? So we're going to go down 1. So notice here's the blue line. We go down 1, okay, right here. And then we rise 6, 1, 2, 3, 4, 5, 6, and go over 1. So this is how they got their blue line, right? And this is their blue line, and this is f of x. So now if we try to graph our f inverse, this guy right here, f inverse of x, let me write that a little better. F inverse of x, that's going to be this red line right here. But I'll just kind of, now again, it's really hard to see, but we're going to rise 1/6. So that's like right here. And then we're going to, I'm sorry, we're going to put our y-intercept as 1/6, and then we're going to rise 1 and run 6, right? Because here's our slope. This is 1/6 x plus 1/6. So our slope is rise 1, run 6. So I'm going to go up. So 1, 2, 3, 4. Wait, is it negative? No. Oh, no, I'm going the wrong way. I'm sorry. I was imagining things right now. So I rise 1 and I go over 6. 1, 2, 3, 4, 5, 6. Right there. Okay. And that's how they got their red line. Now notice they are reflections or mirror images of each other across this line right here in the middle. This line, y equals x, reflects these two graphs across each other. And this is a special relationship between inverses and their original function. So functions and their inverses always have this relationship. They will always be reflections across the line y equals x, always. okay? So this line isn't really there, right? This line doesn't exist, but they're just showing you that if you have this invisible line right here, y equals x, if two things are inverses of each other, then they will reflect across this. They will be mirror images across this line, okay? So that's another relationship, is they are reflections or images of each other reflected across this line, y equals x. So here we know that the domains and ranges flip-flop. Here we know that they're reflections across this, but a lot of it has to do, or almost all of it has to do with the way we built it. We interchange the x's and the y's, so that builds this special relationship between an inverse and its function. So notice that the graphs of f and f inverse in the previous example are mirror images of each other, and the mirror is the dashed line y equals x. Like I was saying, that's the kind of like that reflection line. This is true for every function and its inverse. For this reason, we say that graphs of f and f inverse are symmetric about the line y equals x. Okay, so graph the inverse functions, function graphed in blue and the inverse graphed in red. Okay, so we already did that. All right, let's move on. Determining whether functions are inverses of each other. All right, so what page is this? Let me just kind of get caught up here. Sorry about that, guys. Oh, we're done with that. Okay, so now I'm on 17. So we're almost done. So this is definitely, you guys, we just did a little bit of practice. In fact, I'm going to try to bring up one of your homework problems as well, just so we can kind of have a little bit more practice. So once I finish with this, I'm going to do a homework problem from what you guys have been working on. Okay, so if f is 1-to-1, then the inverse of f is the function f inverse such that f inverse composed with f of x equals x, and f composed with f inverse of x, okay? So that means that when you do composition of functions of a function and its inverse, you should always simply get x as your answer, okay? So that's what this is saying, all right? And both ways, it should go both ways. In my experience, I mean, maybe I haven't tested enough of them, but I feel like if it works one way, it works the other, but you should still check both ways, okay? All right, so let me get going on this blue here. So it says, show that if f of x equals 4x minus 1, that f inverse of x is equal to x plus 4, okay? So we're gonna do this composition of functions, okay? So let's do f of f inverse of x, okay? So that means that I'm going to take f inverse, which is x plus 1 over 4, and I'm going to put it in for x. So that means I'm going to do f of x plus 1 over 4. So that means everywhere that I see an x, I'm going to put an x plus 1 over 4. So this goes right in there. So this is going to be 4 times x plus 1 over 4 minus 1. And this would be, so the 4s would cancel, and this would be x plus 1 minus 1, which equals x. Check. Now let's go the other way. Let's do f inverse of f of x. So that means I'm going to do f inverse of, and now I'm going to take 4x minus 1, and I'm going to plug it in for x right there. So this is going to be 4x minus 1 plus 1 all over 4. Okay, so this will become 4x over 4. So this will become x. Check. And notice they said that's exactly what was supposed to happen. So if you can get x as your final result by doing a composition, that means they are in fact inverses of each other. So we would say they are in fact inverses, and we just proved it. Okay, and because they are inverses, we know that they are now reflections across the x-axis or across the y equals x line. They're mirror images of each other across that line. We know that the domains of f will become the ranges of f inverse, and we know that the range of f will become the domains of f inverse. So we know all of that just from knowing that we've proven that they are inverses of each other. So let me find a problem for you guys from your homework. So I have this one from 9.2. Let's see here. Okay, sorry. So let's do find the inverse. Let me see if I have a better one than this. Yeah, find the inverse of f of x equals the cube root of x minus 1. Okay, so first thing we have to verify is that it is in fact a one-to-one function. Okay, so I'm just going to take out my calculator and I'm going to plug in the cube root of x minus 1. Okay, so you guys should probably know this graph by now. This is this graph right here, right? So you see it in your calculator. Remember, it's basically the basic cube root just shifted. So we're just going to say, I'm just going to eyeball it and just say that's not a very good graph of it, but you guys get the idea. Oh my goodness, I can't draw. Okay, so it's shifted over a little bit. It's shifted over to 1 right here because of this horizontal shift. But what we can tell just by looking at this is definitely a one-to-one function. It passes the horizontal line test, and it also passes the vertical line test. Now, the reason you want to know if it's one-to-one is because one-to-one functions, their inverses are also functions. And remember, that's what we're concerned with. We're concerned with inverse functions, okay? So let's see here. So we're going to find the inverse. So we're going to follow our steps. So step 1, replace f of x with y. So this is cube root of x minus 1. Step 2 says replace or interchange the x's and y's. So this will become x equals the cube root of y minus 1. Then we know that we have to solve for y now. So I am going to cube both sides. So this will become x cubed equals y minus 1. Remember, these kind of cancel in a way. They're inverse operations of each other. So then we solve for y. So we have x cubed minus 1 equals y. So then it says the last step, call y f inverse, and we have x cubed minus 1. Okay. Now, if I graph x cubed minus 1 on the same graph on my calculator, so I'm going to do x cubed minus 1, they should be mirror images of each other. So again, I'm not perfect at drawing, but I'm going to try. So it does something like this. I'm trying, guys. It's not, oh man, that's really bad. I'm sorry. I am very bad at drawing. That's why I'm a math professor. Okay. Or math instructor. Okay. So there we go. So we have these mirror images of each other. Okay. And what I could do if I wanted to verify, now this is not necessary because we found the inverse and we recognize that it was a one-to-one function. So the inverse is now a one-to-one function. But I could use this little test up here to verify and make sure that they are inverses. So just to show you guys. So I could take and I could do f of f inverse of x, and that would become f of, and then we said the inverse was x cubed minus 1, right? So this would become, I'm going to take x cubed minus 1 and plug it right there. So this would become the cube root of x cubed minus 1. Oops. Did I do something wrong here? Yes, I did. Look right here, guys. I made a little brain typo. This one, when I moved it over, had to become +1, right? +1. So this should be a +1. Please fix that in your notes. I kind of messed that up. Okay. Did I graph that right on my calculator? Let's see. I'm just looking at it to make sure I didn't draw like too bad of a graph. I knew what it was supposed to look like, but yeah, the calculator misled me. Sorry about that, you guys. So it's supposed to be something like, I just thought it was because my drawing was so bad that it wasn't working. It's supposed to be something like this. And then right there, it does that. So then we can see right here, if I draw this line right through the middle, again, bear with me on my drawing, they are reflections across that line. So that reaffirms it. Okay, I'm sorry about that. My drawing was so bad last time. I thought that it was fine, but it actually was slightly off because I did a little typo right here. So let me fix this real quick. So fix this real quick. That should be x plus 1. That should be x plus 1. So let me just start over from here. So I'm going to take this and I'm going to plug it in right there. So this will be f of x cubed plus 1. So then that means that I am going to have the cube root of x cubed plus 1 minus 1, which would be the cube root of x cubed, which is just x. Check, right? That's what was supposed to happen. Now let's go the other way. F inverse of f of x equals f inverse of, now we're going to do cube root of x minus 1, and we're going to plug it in now right there. So this will become cube root of x minus 1 cubed plus 1. Well, those will cancel. We're left with x minus 1 plus 1, which is equal to x. Check. Remember, if you get x at the end, that means that they were in fact inverses when you do a composition of functions. So hopefully this helps you guys out with the homework. Let me know if you have any questions in our meeting. I will see you then.